I will talk about a new Hamiltonian Monte Carlo method developed for efficient sampling from multimodal target distributions. I will denote the unnormalized target density by pi of x, and negative log of pi is defined as a potential energy u, which is a function of the variable x. HMC uses an auxiliary momentum variable p, which has the same dimension as x, or alternatively uses an auxiliary variable, velocity variable denoted by v. The momentum p and the velocity v are related by this linear equation p equals mv, where m is a d by d positive definite matrix. This matrix represents the mass of the particle. In this work, it was more convenient to use the velocity variable v instead of the momentum p, so I will use mostly x and v in this talk. The kinetic energy is defined as k of v, which equals 1/2 v transpose mv. The Hamiltonian is defined as the sum of the potential energy u and the kinetic energy k, and it represents the total amount of energy a particle has. In the Hamiltonian system, a particle moves according to these Hamiltonian equations of motion, which say that dx over dt equals the velocity v, and dv over dt equals negative m inverse times partial u over partial x. The solution to these Hamiltonian equations of motion is called the Hamiltonian flow, which is denoted by capital phi. So phi of t maps the initial condition x0 and v0 to xt and vt. The Hamiltonian flow has the property that it conserves the Hamiltonian, or the total energy, and it also has a property that the volume element is preserved along the path, so that dx0 dv0 equals dxt dvt. The flow is often numerically approximated by the Liebfraug method, and the numerical approximation will be denoted by capital psi sub t. The Hamiltonian Monte Carlo algorithm works as follows. Given the current state of the constructed Markov chain, say xi, we draw the velocity variable from the multivariate normal distribution with covariance m inverse, and then numerically simulate the Hamiltonian dynamics with initial condition xi and v. If a uniform 0-1 random number lambda is less than the ratio of the extended target density, which is given by e to the minus the increment in the Hamiltonian, then the end state xt is accepted and taken for the next state of the Markov chain xi plus 1. Otherwise, the chain stays at its current position. The Hamiltonian Monte Carlo algorithm struggles when the target distribution is multimodal for the following reason. Since the total energy, which is the sum of the potential energy u and the kinetic energy k, is conserved, the maximum amount of increase in u along the path is bounded by the initial kinetic energy k of v0. This schematic diagram illustrates this point. On the left, you can see the potential energy function u, and the value of u is higher in the middle than either side. The target density pi, which is equal to e to the minus u, has this bimodal shape. In order for the simulated Hamiltonian path to move from one node on the left to the other on the right, the simulated particle should climb up this potential barrier. In other words, the initial kinetic energy should be at least as large as the height of this potential energy barrier. Unfortunately, the initial kinetic energy follows a half of the chi-squared distribution with d degrees of freedom, where d is a space dimension. So the probability that the initial kinetic energy is greater than a certain number, say delta, scales exponentially as delta increases. Consequently, as the two modes are separated by a high potential energy barrier, the probability that there occurs a transition from one mode to the other decreases exponentially. Let's consider an approach that tries to tackle this issue by increasing the initial kinetic energy. For instance, we can increase the mass of the particle from m to say m tilde, which is equal to alpha times m, where alpha is greater than 1. So the kinetic energy is increased by a factor of alpha. So we are making a simple modification to the HMC where the proposed candidate is obtained by simulating the Hamiltonian dynamics with increased mass m tilde. I will call this approach mass-enhanced HMC, and this is a toy algorithm that works well for some multimodal distributions but not very well in others. The proposed candidate xt is accepted if a uniform random number is less than the ratio of the extended target distribution, where this acceptance criterion depends on the original Hamiltonian h that involves the unaltered mass m. Here is the pseudocode of this toy algorithm, which is the same as the pseudocode for standard HMC, except for two differences. First, the Hamiltonian path is simulated with mass m tilde. Second, instead of simulating the path for a set time length, the simulation is continued until an acceptable state is found. It can be shown that if we use the same uniform random number lambda to determine the acceptability of every state, then the algorithm can construct Markov chains whose stationary distribution is equal to the target density pi. This algorithm constructs Markov chains that frequently jump between modes for some special cases of high-dimensional multimodal distributions, such as a mixture of Gaussian distributions, where the covariance matrices of all mixture components are the same. However, this method does not work well in general when the mixture components' covariances are not the same. Now I will explain the main algorithm. The reason that the previous toy algorithm does not perform well is that the amount of increased kinetic energy at the beginning gets evenly distributed between the kinetic energy and the potential energy. Thus, the Hamiltonian path may never reach a region with low potential energy where the state is acceptable. A way to solve this issue is to increase the mass slowly along the path, and then once the mass reaches the set maximum, we decrease the mass again. Then at the end of this cycle, the path can settle down at a point with low potential energy. The mass m is modulated along the path this way, e to the 2 eta m, where eta is a time-dependent mass modulation schedule. For numerical simulation, we use a discrete sequence of mass modulation schedule of this sinusoidal form. Here is an example. The target distribution is a mixture of two Gaussian distributions of dimension 10,000. The left panel shows an example trajectory, which slowly spirals out of the initial mode and then spirals back into the other mode. The right panel shows a trace plot of a Markov chain. You can see that there occurs frequent hopping between the two modes. The pseudocode is similar to that of the toy algorithm that was introduced earlier. The main difference is that for each leapfrog jump, a different mass is used. As an application of our method, we considered a sensor network self-localization problem. There are 8 sensors of unknown locations, x1 through x8 in the unit square, and there are 3 additional sensors with known locations in the same unit square. Pairwise distances between the sensors are observed with a probability that decreases exponentially with the square distance. If the distance is observed, then the measurement has a Gaussian error. We ran 12 parallel chains with varying initial conditions. The estimated marginal distributions for the 8 unknown sensor locations are shown in this figure. The real locations of the sensors are marked by the numbers on the plot. You can see that the distribution is clearly bimodal. For example, the estimated locations for sensor number 3 is on this area and on this area. This bimodality comes from the fact that the sensors of known locations, that is sensor 9, 10, and 11, happens to be roughly on a straight line. Therefore, the sensor configurations that are mirror images of each other about this line are almost equally likely. But these two modes are separated in the 16-dimensional target space. All 12 parallel chains were able to identify both of the sensor configurations, and there occurred frequent hopping between the modes. As a summary, I'd like to compare our method to other MCMC methods that were developed for multimodal target distributions. Darting Monte Carlo is an algorithm that facilitates direct jumps between the modes of known locations using independence metropolis Hastings sampler. Simulated tempering is a strategy that targets a mixture of tempered distributions at various temperature levels. The Markov chain occasionally jump between different temperature levels, and at high temperatures, the chain is more likely to move between the modes. Our method, mass-modulated Hamiltonian transitions, can be considered as a hybrid of Hamiltonian Monte Carlo and tempered transitions developed by Neal in 1996. When the mode locations are known, darting Monte Carlo cannot be implemented, and the locations have to be first identified using other approaches such as deterministic gradient ascent. Simulated tempering and our approach has clear advantages in this case. Darting Monte Carlo does not have a good dimension scaling property. Simulated tempering often uses random walk type proposals, which are known to be less efficient than Hamiltonian Monte Carlo. Our method uses the gradient information of the log target density and can efficiently sample from high-dimensional multimodal distributions. In terms of the time required to obtain a sample point, darting Monte Carlo has the advantage over the other two methods because the jump is attempted by a direct proposal made by an independent metropolis Hastings sampler. For simulated tempering, one has to wait until the chain moves from the lowest temperature level to the highest temperature levels and move back down to the lowest temperature level again. Since the transitions between the temperature levels happen in a random walk-like fashion, and because the valid samples are only obtained at the lowest temperature level, the runtime per sample is likely to be much longer than darting Monte Carlo. Our method modulates the mass in a systematic way, and modulating the mass can be shown to be numerically equivalent to modulating the temperature levels. Thus, the random walk-like behavior on the temperature is avoided, but the mass modulation typically has to be carried out relatively slowly, and for each new sample, an order of 1,000 real-through jumps may be necessary in practice. In terms of how readily the method can be adapted for a given distribution, darting Monte Carlo is again at a disadvantage because the independent metropolis Hastings sampler has to be constructed only after approximating the target distribution by, for example, a mixture of normal distributions. For simulated tempering, the relative weights at different temperature levels have to be carefully tuned for reasonable efficiency. The Wang-Landau algorithm develops an adaptive method for tuning the weights for the tempered distributions, but it takes time to obtain a favorably adapted set of weights. Our mass-modulated Hamiltonian transitions are relatively simpler to tune the algorithmic parameters. This difference in adaptation difficulty makes a practical difference in the Gibbs sampler settings where the target distribution changes frequently.